So I died then. So it was really awkward. My whole one was supposed to angle up, but I just couldn't do it. Right. And so it happened today. But I didn't die yet.
Are you guys ready?
Yes, sir. No, it's not bad.
All right, so first order of business, this meeting is being recorded for people not here, so you people behave yourselves. Jared.
Wait.
You recorded for me when I was here.
You didn't ask.
Yeah, I considered it a free day.
Okay. Your choice, I guess. Yeah, if you're ever gone and you want me to record, you have to let me know ahead of time, but I'll record it if you want. I'm not totally sure how useful they are, but, I guess they can't be unuseful. Okay. Anyway, so today, as all Fridays are, right, but especially today is Friday Fun Day. We've gotten to the interesting part of Chapter 5, where finally we can start to see statistics in its full usefulness as a way of testing claims, testing truth claims. So if you look at the first page of this handout, there's nothing about truth claims there, but when we get to the second page, now we can start testing claims people have made. So I'm pretty pumped, and I can tell all of you are also pumped, right? I guess, yeah, there we go. I can see your body language and your bright eyes. Yeah, so anyway, this is nice. This is really, so this Friday and all of next week, there's fun. Fun in here, and then when you're not in here, you're on spring break. Is there a better week than that? All right, so anyway, so we're going to be spending 3 days talking about the central limit theorem and what it can do for you. That's why there's a part 1 up here. Your book, so again, I like it a lot in certain ways. It has a lot of really nice examples. I kind of like the flow of the material, things like that. But then in other ways, it really just falls flat on its face in very strange ways. The book does not play up how useful this is. And if you read section 5.4 and 5.5, it's very short. It just doesn't show you in all of its glory why statistics is useful. I'm not sure why they made that choice. But anyway, so we're doing more, we're going to go more in depth than the book does, because the book stops short in some very strange ways. Anyway, what we're going to do today, the book does, though. So if you want to reference the book for this section, you can. Okay, anyway, so the summary of the section is we're going to cover the central limit theorem. The central limit theorem has many different parts. So this is part 1 of it. Do part 1 and part 2. It has many different parts based on what kind of claim you want to test, basically. So we'll see that as we move through this section. Anyway, so here's the basic idea. Suppose you have a random variable x modeling something, dice rolling, whether or not somebody got sick, whatever. It can represent anything, called, wait time, or whatever, right, on hold, whatever. This variable can have any kind of probability distribution you want. So if you draw the density function, it doesn't have to be a bell curve. It could be, like call center 1 was like a hyperbola going down or something, right? So the graph can be anything. What the central limit theorem says is, if you create a new variable by adding x to itself a bunch of times, that new variable will be normal. So if you take something that's not a bell curve and add it to itself a bunch of times, it becomes a bell curve. And then you can use a normal distribution calculator. And same thing if you take an average. If you add x to itself a bunch of times, take an average, that random variable will also be a bell curve, even if x originally did not have a bell curve. So that's really nice. Okay, so here are the formal statements. So if x1 up to xn are independent random variables, each with the same average and each with the same standard deviation. So again, in particular, these guys could all be literally the same. All right, but the theorem is stated a little more generally. Then if you create the summation variable, this kind of thing we've looked at many times before, right? That will have a normal distribution, so it'll look like a bell curve. The theorem puts the word approximately in here to cover its basis, okay? So it might not be a perfect bell curve, but it'll be good enough to use the calculator. And the average value will just be, take the old average value and scale it by the number of times you added. Okay, that makes sense, right? Again, this is, I keep referring to it as Jarrett's theorem, right? That's all it is. You take the old average and just multiply it by the number of times you add. And the standard deviation is not old 1 over root n. So this is a modified version of square root law, but the old standard deviation times root n. So you still see a square root there. Okay, so finally, when n is sufficiently large. So if x1 is not normal, then when you do x1 plus itself right here twice, you might not get a bell curve out of that. But if you keep doing it enough times, you'll see something normal. So You might have to add the variable to itself 30 times, I don't know, to see a bell curve. And then central limit theorem part 2 is the same exact statement, except now I'm doing this average variable, right? I add everything up and then take an average. And now we kick into the square root law from last time. We had a theorem that says the expected average of the average is the old average. You know, average of average is the same average. And the standard deviation is this square root law standard deviation from last time. So the key new thing is you get a bell curve out of this if you do this enough times, if you sample enough times. That's what it says. Questions or comments on what that says? Okay, well, one question you should have is like, wait, what? I'm not totally sure I understand what it says. It's kind of a weird statement, you know? So usually students have, when I first show this to them, it's hard to even articulate what a question is. Like, okay, I've read this, but like, what does that mean, you know? So let me just show you how this works. So I'm gonna do something, or start with something familiar here. So X is the roll of a single 6-sided die. Then the average is 3.5, right? The average roll is 3.5, and here's the probability density function. This is a discrete example, right? I'm starting with something discrete. There's only 6 outcomes. Everybody okay with that? Yeah. Now in the homework, if you were asked to graph this, let me just show you what you would do. Bless you. So this is discrete, so you're not going to draw a curve per se. Let me just show you what you do. So on the horizontal axis, you have the individual outcomes, 1, 2, 3, 4, 5, 6. And then you basically draw a scatter plot. So here's a graphical representation of that probability density function, right? If you input an outcome, there's its probability. Are you okay with that? So, you know, if you had to do some curve fitting here, if you had to like smooth this out, the curve you would fit to these points does this. Horizontal line, right? Horizontal line is most notably not a bell curve, right? Everybody agree with that? Okay, so now let's take this X and start adding it to itself, or taking averages, whatever. Now, I'm not going to do it very far. I'm just going to do it twice. Let me get this reshared. Okay, so now let's do X plus X, right? Roll 1 plus roll 2. The expected value is now 7, right? Number of rolls times the original expected value. And here are what the probabilities look like. This should be very familiar to us because we've used it so many times, right? The outcomes are 2 through 12. Here are the probabilities. Everybody see that? It's, of course, no longer a flat line. What does it look like? Yeah, it looks like a bell curve, actually, right? Now, it's not a perfect bell curve because it's actually like literally a pyramid, right? And bell curves are smoother, but it's basically a bell curve after just doing this twice, right? So again, we started with a variable that was not normal at all, you know, which sounds like a mean thing to say about it, right? You abnormal, right? Probability density function. And then we just took that variable and added it to itself, and we got something that looked pretty normal, you know? Everybody see that? Central limit theorem says this will happen. And then here's the same thing for adding it to itself twice and taking an average. So here are the possible averages of 2 rolls. Did I agree with that? You could roll a 1 and a 1, and then the average is 1, right? Did I see that? You can roll a 1 and a 2, and the average is 1.5, and so on, right? You can roll a 6 and a 6, the average. So here's all the possible averages. The probabilities don't change though, right? Because to get an average of 1, you must roll a 1 followed by a 1. Everybody see that? Only 1 out of 36 ways to do that. To get an average of, say, 2, you could roll a 2 and a 2, or a 1, 3, 3, 1, you know? Did I see that? So this curve here and the one above it, really the only difference is that here, see, the outcomes are pretty spread out, right? So the data is getting wider, you know. But here, you know, I used to run from 1 to 6. I still run from 1 to 6, but things are getting crunched, you know. There used to be a sixth of the data right here, right? At 1, there used to be a sixth of the data there. Now it's 1/36 of the data there, right? So you can see that sort of crunching in action, that sort of minimizing of spread. Oh, sorry. Okay, so anyway, here's sort of the central limit theorem in action. We started with a variable that was not normal. We added it to itself. We added it to itself and took averages, and we got these density functions that look a lot like a bell curve, you know. Now in practice, we got a bell curve looking thing emerging really quickly, right? We only had to do 2. So the central limit theorem doesn't say that's going to happen. You may have to do it more times, right? But the more times you do it, the more normal things get. And just to show you how this can work with something a little more artificial, maybe. Okay, so suppose you have a die, but it's weighted. It's weighted towards the smaller numbers, right? Now, do you guys agree this isn't normal at all? This looks like one of those call center wait time things, right? So if you were to draw a scatter plot, like high, like it just sort of die down like this, right? Okay, so again though, we can build a probability density function for, I did the average. If you do the not average, just the sum, it's the same numbers, just the outcomes stretch farther. But anyway, here's the probability density function now. So first let me ask you guys, if I forced you to go from this table to this table, and I didn't have these probabilities filled in here, like that's gone, so on, how could you get that number? Where'd that number come from? I'm sorry, say again. Okay, so you have the exact right idea. I'm gonna share this. Okay, so now we're thinking about eraser. Anybody see an eraser? Okay, so for that weighted die, we have to think about rolling it twice and getting an average of 1. So how do you get an average of 1 if you're rolling that die twice? You have to roll a 1 and a 1, right? Everybody see that? So if you think about probability, roll 1, roll 1. How do you get that probability? Yeah, if you want to, you can think of it as a chance tree, right? It's like roll a 1, roll another 1, and it's just 0.25. You okay with that? So this is just 0.25 squared, which is what I hope I've written there. Let's maybe not check, maybe just trust. I think that's 0.25 squared. It is? Oh, that's good. Okay. Anyway, that's how you can fill in this table. So let's just do one more. Suppose you want to think about the probability of getting an average of, I don't know, it's about the average of 2, maybe. Okay, how many ways, or how could you get an average of 2? What do the rolls look like? You could roll a 1 and a 3, right? You could roll a 3 and a 1, the other way. 2 and 2. There are 3 ways to do that, right? How do you get the probability of this way? Sorry? How do you get the probability of rolling a 1 followed by a 3? Same thing again, right? You do 0.25 times 0.18. Just read off the numbers from the original table. And then this will be the same, right? Same thing. Just you swap the places, right? And then what's the probability of 2 followed by 2? 0.2 times 0.2, right? You just add those guys up. And that's how I got that 0.13 in the table. So in the homework, there's a problem similar to this, but instead of a 6-sided die, it's a 4-sided die, you know, so you don't have to like do this a bunch of times. But again, just to see this normal curve showing up, right? So again, we started with a function, probability density function for x that looked nothing like a bell curve at all. But if you scan your eyes, like if you made a scatter plot of these guys here, right? Can you see what kind of shape is emerging off of that? Yeah, it's bell curve-ish, right? It's definitely like low, high, low, right? So even though all the data used to be weighted like right here, right? When you start taking averages, whoop, all of a sudden all the weighted data is right here in the middle, you know? So the central limit theorem just says that kind of thing happens always, you know, if you do this enough times. And again, here we only had to do it twice. Okay, so that's what the central limit theorem is saying. And as the last note, before we pause and move on to the next one, these two variables here, it says, are normal if n is sufficiently large, you know. The central limit theorem doesn't say how big n has to be. So it's possible you do it twice and you don't see something that looks normal. It's maybe more normal, but not normal looking. So then maybe you got to do it 3 times, 4 times, whatever. So in practice, I'm not a statistician, so I have to be a little careful, but my impression is that in practice, for any application you'd ever use, if n is 30, you're fine. So maybe it doesn't work on 2, maybe not on 3, but by the time you reach 30, you're going to see a bell curve for anything you'd run across in practice. So you can just kind of, I didn't want to put that in the handout because I don't want to get in trouble, like a statistician finding these or something, but anyway, if n is 30, you're fine. Usually if n is like 3, you're fine, you know. But you can construct wacky examples where n equals 3 still isn't big enough. Okay, so let me pause here and ask. Any questions on what the theorem is saying? Is it clear how these examples illustrate what the theorem is saying? Okay, so now a question you should have is, what does this have to do with anything? Like, I thought we were gonna like evaluate people's claims they were making, right? So what does this have to do with that, you know? And the answer is, well, can you just wait a second, you know? Okay. So for the rest of this section, so for the next 3 days, we're gonna be doing something called hypothesis testing, which is a way of evaluating claims. And before I dive into the example in the handout, I wanted to show you how the logic works. Because the logic is fairly subtle if you're not used to it. And a lot of times, you know, before I worked here, I taught an intro to stats class to first years, and this was always the biggest stumbling block for them, understanding what the logic was, because it is kind of subtle. So before I do the one on the handout, let me give you an example. And the sort of logic you should have in your head is proof by contradiction. So I don't know if you like that language or not, but that's how the logic works for hypothesis testing. So we'll come back to that in a second, but let me make a claim and we'll think about how you could evaluate it or not. Okay, so what claim do I want to make? Okay, so when all of you look at me now, what do you see? You see a sad, broken old man, right? Isn't that what you're thinking? Over 30, like nothing left, right? Now, back in my day, though, I was not a sad, broken old man. I was full of youthful vigor like you people, you know? And one thing I did was I played basketball all the time. And I was pretty good. Like, not actually good, but like, you know, if I played pickup ball against like an 11-year-old, I could destroy them, right? That kind of thing. So in particular, suppose like you met me at that age and I made this claim to you. I say, I'm really good at free throw shooting, okay? So here's a claim. I'm a 90% free throw shooter. Right, there's a claim, right? So I'm really good, is what I'm saying. You know, 90% is pretty good. Okay, well, suppose you doubt that claim, or you want to evaluate it somehow. How would you evaluate it?
See how he can breathe.
Yeah, you would say, you know, I doubt that, right? And then I would scream at you, insolence! Like that, right? And I'd grab you by the ear, and I'd drag you out to the Maybe Center, right? With their basketball goals, okay? And then you can watch me shoot free throws, right? So I agree with that? Okay, so let's think about some outcomes that can happen. Those don't have a ton of time, so I'm going to shoot 20 free throws, just 20. Okay, here's case 1. Suppose I make 17 of them. What do you think about my claim? Did you get up in my face and scream that I'm a liar?
You're a liar.
Yeah. Well, Trenton claims you do that. Yeah. I mean, does making 17 of 20, that's 85%, right? Does that disprove this? I mean, not really, right? Because 20 is not that big of a sample size, and a 90% free thrower will certainly make 17 out of 20 sometimes. You know what I mean? So it's not like I've proven my claim, but you can't, we haven't disproven it, right? You can't say to me, oh, this is false, you know? I know it's false because you didn't make 90% of them, right? So the way you would, the logic that's working here is like this. This is why it's a proof by contradiction. You say, okay, I'm going to take your claim seriously. Let's assume that this claim is, let's assume this is true, right? I'll enter your world, right? Or you're a good free throw shooter. And then ask myself, does this data sort of match up with the claim or not, right? So what we're asking actually is this. This is why it's in a probability class. So given the claim, what's the probability of seeing the data I just saw? So all of hypothesis testing runs off of a question like this. Okay, so assuming this claim is true, so it's like I'm with you for now, right? Assuming this is true, what's the probability I would see data like that? So if this probability is super, super low, what you're saying is, okay, if your claim were true, the probability of seeing this is like minuscule, that's doubtful, right? Did I see that? And by the way, this is called a p-value. A term I'm sure you've heard before, right? It's a probability of seeing data like what you're seeing given some sort of truth claim. So who knows here, right? But if a 90% free throw shooter, sorry, let me phrase it this way. Suppose somebody is a 90% free throw shooter. What's the probability of seeing data like this, 17 out of 20?
Not the highest, but not the low.
Yeah, it's not going to be like maybe the maximum or something, right? But it's not going to be low. Everybody agree with that? You think a 90% free throw shooter make them shoot 20 free throws, the expected value is going to be 18 out of 20 probably, right? But you're going to see 17 out of 20 all the time probably, right? Everybody agree with that? That's the logic here. So basically, given a claim, you either call the person a liar or say this is false, or you say, well, I don't have enough evidence or information to disprove your claim. Okay, so you're not going to tell me, oh, like I believe you necessarily, but you would at least say I can't disprove you. So there are two outcomes in a hypothesis test. Let me just bank them over here. And then we can do this example. There are two outcomes. You can either reject the claim, so call them a liar or something, right? There's one reaction you can have, or statisticians call this, let me try this, fail to reject the claim. So with hypothesis testing and statistics, you never come out and say, I believe you. You say, I don't disbelieve you. You know? I can't disprove you. That's what this is saying, right? This is saying I don't believe you. You know? I don't believe you. I don't disbelieve you. Like I'm not going to reject what you're telling me. Yeah.
So if you would only make two of them, for example, would that be weird?
Yeah, right. Yeah, so let's move on to a situation like that, right? So now I've made this claim, and I did it really aggressively, remember? I dragged you all the way down from this classroom to a place that might actually be more temperate, right? Maybe it actually feels nicer down there. Anyway, suppose now I make, I don't know, 8 of them. You know, right? So you could, again, run the same logic and be like, okay, if you were a 90% free throw shooter, like assuming that's true, what's the probability I see you make 8 out of 20? Is that a high probability or low probability? Low, right? And on some level, this makes intuitive sense, right? Like the farther this number strays from 18, right? The more evidence you have that I was lying, right? So again, it's worth pointing out, though, that it is possible that this claim is true. It's possible this is true, and yet I do this. Maybe I'm having a super bad day. I'm super unlucky, you know? Like maybe all 12 of my misses were like the in and out ones, right? You know, whatever. But still, this p-value is very low here, right? That thing gives you evidence to reject my claim. So the smaller this probability gets, the more evidence you have to reject what I said. You okay with that? So this p-value here is probably less than 1% or something, you know, it's pretty small. Whereas the p-value of the red was, I don't know, who knows, right? But maybe like 20% or something. It's not that low. That's the logic of hypothesis testing. Somebody makes a claim, you take it seriously. You're like, okay, I'm with you. I'll assume this claim and then ask myself, given that claim, what's the probability I see the data I just saw? Right? And if that probability is super low, you have evidence to reject. You have evidence to call them a liar. That's the logic. So if you ever get lost in the logic of any of these problems, hopefully this is illustrative, right? You can always come back there and be like, well, what was happening in that example? Okay, so here's sort of our first real example. And sorry. For some reason, when I'm connected to the Apple TV, you guys on Zoom are super quiet. So maybe let me disconnect from the Apple TV. Was somebody yelling something?
I heard Shane call you a liar again, but other than that, no.
Shane is very aggressive towards me. And I don't know where the hostility comes from.
That's not true.
Okay. Okay, so let's look at these couple of examples, then we'll call it a day on Friday Fun Day, right? Now, this first one is just a warm-up example, and the second one's a sort of a real example, right? But let's just see if we can process this warm-up example and the logic behind it. Okay, so a casino owner runs a game that involves coin flipping. He flipped a fair coin 10,000 times and got 5,227 hits, right? So the question is, do you believe that? Fair coin doing that, you know? And on its face, that seems believable, I guess, because we're expecting like half to be heads, right? And this is roughly half, right? So on its face, this seems believable, but let's see, is this believable? Okay, so again, I'm not gonna read all this to you, but to test a claim like this, you have to sort of take the claim seriously and ask, you know, assuming the coin is fair, what's the probability I see data like this, you know? So you assume a claim and then ask, what's the probability I see what I just saw? If that probability is super low, you can be like, oh, that claim's probably false. Okay, so in statistics terminology, have you guys heard this term before, a null hypothesis? Okay, it's fine if you haven't, but that's sort of like the default claim that's being tested. So here we're thinking about the coin being fair or not. So we're gonna assume the coin is fair, and then ask ourselves, assuming the coin is fair, what's the probability I see this data? Okay, so now you have to sort of like, what's the word? Rigorize all this, mathematize all this, you know? If you want to use the central limit theorem, which we've forgotten about for a while, right? Central limit theorem was like, hey, you got a variable with a average and standard deviation, you want to add it to itself, take it, blah, 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 right? It was all this. Then you get something normal. Where's all that, you know? So the main challenge in a problem like this for us is like, how do you kick into this sort of framework, you know? As with many problems in this class, right? It's more about finding the right story to tell, the right framework, and you can kick into whatever theorem we have. Okay, so here, I'm gonna let X represent the result of a single coin flip, and I'm gonna have it give two outcomes. So a single coin flip has heads and tails, right? But I need numbers to do anything here, right? So instead of H and T, I'm gonna use 0 and 1. I'm interested in heads right now, so I'm gonna count the number of heads. So I'm gonna let X equals 1 if I get a heads, 0 if I get a tails. Okay, so I'm gonna make two claims here. The average value of X is 0.5. Why is that? You're flipping a coin, right? But I mean, there are like crappy coins, right? Where you might not get an average of a half here. Why can I definitively say right now the expected value is 0.5? Yeah, I'm assuming the coin is fair right now, right? I'm entering that world where the coin is fair, you know? So that's how I can just say right now, like I'm with you, I'm gonna assume what you're saying is true, and then now I have an average of 0.5, right? Everybody see that? Okay, the standard deviation, this formula comes from last week. You could just, since these numbers 0 and 1 have equal weight, you could just ask a calculator standard deviation 0 and 1, sort of overkill. But anyway, this formula here, the square root formula, is from a previous day. The standard deviation of a discrete variable is where I got this from. So outcome minus average squared times probability of that outcome, plus next outcome minus average value squared times probability of that outcome. you remember seeing a formula like this? Okay, so again, it's on a previous handout. You can grab it if you want. And if you ask to calculate what all that is, it pops out a half. So the average value is a half and the standard deviation is a half. It's what? Oh, okay. Sorry. I thought you said literally none of this makes sense. I thought, oh, okay, well, better back up. Okay, so the question is, we don't care about a single flip though, do we? Right? This dude flipped the coin 10,000 times. So I claim we care about this variable here, this y, which on my screen is highlighted, but not on your screen, whatever. So this, right? I care about this. Oh, everything is frozen. All right, so I'm going to disconnect and then come back. Oh, it disconnected for me. Okay. Man, it's really having trouble today. All right, and of course it has trouble on days when like I really actually need Zoom up and running. So Apple TV is like, oh, I'm scared, you know, I don't know what's happening. And then it throws me off of the Zoom screen share. All right. Okay, so anyway, I care about this capital Y. Do you guys see where that capital Y is relevant? Yes, no. Okay, X is the result of a single flip, right? And X is 1 if you get a head, and that's what you care about, right? Everybody see that? So what are the possible values of this capital X? Oh, sorry. What are the possible values of this capital Y when you take X and add it to itself 10,000 times? Could Y, for example, take on a value of 0? It could, right? How would it take on that value of 0? If you flipped all tails, right? Everybody see that? Like all the values of X are 0 as you go, right? Could Y take on a value of say 20,000? No, right? What's the biggest value Y could have? 10,000, right? For 10,000 heads. And then it hits anything in between, right? Everybody see that? So you're just saying like, flip the coin, flip the coin, flip the coin. You're flipping the coin 10,000 times. And every time you get a head, you're going to count it and include it in that sum. Is that okay? So this is the move we have to make in all these problems. You have to identify the variable that the central limit theorem can help you with. Okay, so to evaluate this dude's claim about, hey, if my fair coin did this, this is the variable you care about. And this is the probability we're interested in. So he got a spike. What's the probability you see a spike like that? And just with Poisson problems in chapter 4, right? You care about the entire tail of data, not just a singleton, you know? So what's the probability you see something high like that? Is how you'd phrase this probability. So you're going to pluck off either a right tail or a left tail of data, depending on the context. Here we care about the right tail of data. Once you have this set up, though, you're basically done. So let me just pause you again and ask, is it clear why you care about this probability? Is it clear why you care about this capital Y? Okay, so now the central limit theorem kicks in because Y was a variable added to itself 10,000 times. 10,000 is way more than 30, right? So we can confidently say the central limit theorem tells us this: Y is normally distributed. Also, its expected value is the original average value times the number of coin flips. So in other words, if you flip a fair coin 10,000 times, you should expect to see 5,000 heads, right? That's all that's saying. And furthermore, the standard deviation, this is a summation variable, not a average variable, right? So I'm using central limit theorem part 1 here, wherever that is. You take the old standard deviation times square root of n, not divided by root n. So that's what's here. So if you ask a calculator for that, you get 50. So those are 3 things you need to know before you calculate anything. Capital Y is normal, so it's a bell curve. It's centered at 5,000, that's where its peak is, and the standard deviation is 50. And then you're basically done. Now I put the integral here just for those of you who like calculus to remind you there's an integral, right? But if you want this number without an integral, where do you go? Very close, yeah.
T, or the normal distribution.
Yeah, the normal distribution calculator, right? And since that thing only goes to 4 decimal places, it's just going to tell you 0 right here, you know? But anyway, all you're saying is like, okay, if that coin really were fair, like you said it was, the probability you see data like this is like basically 0. So I don't know about that claim, man, right? Like you claim the coin was fair. I don't know about all that. Doesn't seem likely, you know? It's basically probability 0. Yeah.
How likely or unlikely that is what the other. Oh wait, no, I'm wrong.
Okay, that's fine.
Is that saying that the probability that he got that or higher is that
Yes.
not just
Yeah, you can't deal with exactness here anyway because it's just, you're modeling with something continuous. But even back in Poisson, right, we would still think about like, well, the probability of a point, an exact point happening is going to be super small no matter what. So you really want to think about like that, right? Seeing a spike like that, a dip like that. So you're always going to pick up a tail. Yeah. Okay, so because this comes up in the homework and because you'll be asked to do this on your exam, let me fully write out in English how you'd interpret this 2.81 number. So if I asked you like, hey, fully explain to me what that 2.81 times 10 negative 16, you would say it like this. You would say, I mean, again, you don't have to tell me my exact language, but something like this. Assuming the coin were fair, the probability of seeing something like 5227 heads and 10,000 flips. And by the way, I'm happy with you guys if you want to. I'm just being explicit here, but you can replace this with a phrase like this. The probability of seeing data like what I saw, you know. Whatever, right? So assuming the claim is true, the probability I saw what I saw, my marker item, is 2.81 times 10 to the negative 6, or from your calculator, right? You could also write this from that calculator. So we know it's never going to be exactly 0, so you want to put something like this, approximately 0, right? But for practical purposes, the probability of seeing data like that is 0 if that claim were true. So we have those two options over there. We can reject the original claim of coin fairness, right? Or we can not reject that claim. Which of those do we choose? Yeah, we say the coin's not fair, probably, right? If you had to choose, you would say the coin's not fair. So you can write something like that. You're forced to give a conclusion, right? You say something like, therefore, you know, I think coin is unfair. That's how you'd unpack that probability. Assuming the claim, the probability of seeing that data is this number. That number is really low, right? So proof by contradiction, you know, like, okay, I assumed your claim and things didn't work out for you, you know, that claim is probably false. So it's a probabilistic proof by contradiction. If you like that language. I don't know if you do or not. Okay, any questions on the logic here, the setup? You guys feel comfortable you could do this on your own? Okay, so this is a warm-up example. Let's do a real example, but the real example is just a warm-up example. Isn't it nice how that works out, right? But the real example is now real, right? This is something that you'd read in a stats paper from the 1950s, I guess, because it's about the polio vaccine. Okay, so the polio vaccine, that Salk one, was one of the biggest clinical trials to date when they did it. Just hundreds of thousands of people took the vaccine in the trial. So here's some partial data from that. So 200,000 children were given the vaccine, 200,000 were not given the vaccine, they were in a control group. So they just monitored if those kids got polio or not. So of the kids who got the vaccine, 57 of them eventually got polio. And the control group, though, was 142. So 57 vaccine kids got polio and 142 of non-vaccine kids got polio. So the question is, of course, does this trial show that vaccine is effective? And if so, is it evidence strong or weak? You know. I should share my screen. Oh yeah, sorry. One last thing I forgot to mention. A good question is how low a p-value is too low, right? That's basically 0, so you can reject. The stats literature has 2 standard thresholds, 5% or 1%. You take your pick, basically, you know. There's no God-given threshold that says a p-value here is too big, p-value here is too small, you know. So anyway. Okay, yeah, so this number is like, it just falls easily under that, so you reject. Okay, so back to the polio example. There are several reactions you can have to this paragraph, and I've listed 2 of them there. So here's a very common reaction. Well, look, 57 kids, 142 kids. What are we doing here? There's hundreds of thousands of kids in the trial, right? That's not enough data, right? 57 kids, you're gonna draw a conclusion off of that? What are we doing? Another reaction you can have is like 57 smaller than 142, right? So it's obviously effective, you know. Everybody see that? There are, of course, many other reactions you could have. One reaction is like this. Polio is fake, you know, and it's just made up by like government agencies to control you or something, right? There's a third reaction, like the polio vaccine has like a microchip in it. Wake up, people, right? I call that my uncle's Facebook feed reaction to this, right? That's like reaction 3, you know. But anyway, I'm just saying there's lots of reactions you can have, right? So the question is, how could you cut through all that? You know what I mean? Is this reaction correct? This actually seems intuitively correct to me, you know, but maybe this one's correct. I don't know. I mean, I do know because I wrote this handout, but anyway. So again, when you zoom out, why do statistics exist? They exist to cut through all this, you know? Who's right here, if anybody? How would you know? You know? Everybody see that? Yeah. So, I mean, drug trials can't run without statistics, right? Providing that evidence. Okay. So let's just do the same example as before, but with this setup here. So in a vaccine trial, the null hypothesis, the default claim, is that the vaccine is not effective. We assume that, okay? And the reason we assume that is because now the vaccine makers have to overcome that, you know? Given a new drug, you should always default to assuming it's not effective and then make somebody prove to you it is effective. Does that make sense? You would never default to, oh, this is effective, and then try to disprove that, right? You got the burden of proof the wrong way around. Anyway, so in any sort of drug trial, here's the null hypothesis. So then the trial has to provide evidence to then reject that claim, right? We're assuming it's not effective. We want to reject that. This gets confusing because there's double negatives, right? We assume not effective, and then we want to prove not that, right? We want to show it's not effective, right? That's what rejection would do. Anyway, so you get, I can't process double negatives myself, so I find this very confusing to say out loud. But anyway, that's always the setup. Okay, so now let's do the same thing, but instead of flipping a coin, we're just measuring polio or not, right? So there were 199 people who got polio, right? 199 kids who got polio. Everybody see that? Okay, so now I'm gonna let X represent the result of a single one of those people. I'm gonna let X equals 1 if the person's in the treatment group. So getting the vaccine is like flipping a head from the previous example. Everybody see that? X equals 0 if the person's in the control group. So if you got polio, but you didn't get the vaccine, I'm just not gonna count you in my sum here, you know? Everybody okay with that? Then here's the variable that I claim we're interested in. Right, we're gonna just add up the results of all 199 kids and see what the result is, you know? So 199 is a possible outcome, right? What would that mean? Everybody who got polio got the vaccine. Whoops, right? I mean, a real crappy vaccine, right? Could also be 0 though, right? The outcome could be 0, which means all 199 were in the control group. Right? Surely that's good evidence for the vaccine. Okay, so let's just walk through this example using the framework of the previous one. So X is the result of a single person, a single coin flip, if you like. Assuming the null hypothesis is true. So assuming the vaccine is not effective. For an individual person, what's the probability? And again, this person has polio, right? What's the probability this person came from the control group, is what this is saying, right? Everybody agree with that? So I present to you a person who has polio now, right? And I ask you, what's the probability they didn't get the vaccine? What do you think about that? Well, I don't think it's particularly contagious, actually. Yes, I guess the right response is immediate disgust at this poor child who's been placed in front of Trevor.
Let me just gather my data up here.
They write out in English, so it's clear what we're doing. We're going to assume vaccine not effective. Okay, so 199 kids got polio. Given kid with polio, what's the probability they didn't get the vaccine? Or if you want to flip this question on the head, you can do the opposite, right? It's probably they did get the vaccine. I don't know. Say again, sorry. So sorry, we're just thinking about a single kid, and we're not processing the data yet, right? So far, we're just processing the claim. So we're testing this claim right now, right? So if the vaccine is not effective at all, I haven't looked at the data yet, you know. If the vaccine is not effective at all, what's this probability? Yeah, just a hat. It's like a coin flip, right? Did I see that? Because if the vaccine is not effective, it's like you're just sorting kids into two groups via coin flipping, right? The polio kids, right? Everybody see that? So basically, this is how drug trials run. They're like, if all you're doing is testing effectiveness, you're like, well, if it's not effective, then of the people who got sick, I can sort them into the two groups by just flipping a coin. And once you have that set up, the probability of X equals 0, so probably a polio kid got the vaccine versus not got the vaccine makes no difference. To use the central limit theorem, now all I have to think about is what's the spread on that data? And again, it's kind of a trivial little computation because there's only two data points, right? 0, 1 with equal weight. What's the spread here? Yeah, same as above, right? You can just import the number from the previous example because under the hood, it's not just coin flipping. So again, this is how, like, if you read the Salk paper or whatever, right, like explaining why he knows the vaccine works, you just see this, you know. I mean, you don't just see this, but we have to finish this off, right? Okay, so now with this in place, we just have to articulate what probability we want and use the central limit theorem, and we're done. Okay, so the variable I care about is y, right? All 199 kids adding up who got polio from the treatment group versus control, right? So what probability do I care about from y's perspective? Well, now we can look at the data, right? We've processed our assumption. What kind of data did we see? Y is representing number of kids in the vaccine group who got polio, right?
57 over 200,000. Or would it just be 57?
Yeah, you just care about what's the probability saying 57 or fewer kids. It's a left tail thing, right? So the right tail thing now. You saw a dip, right? You're expecting to see complete evenness, right? So the 199 kids, you're expecting like a 199 split, right? You saw something way smaller than that. So let's think about the probability of getting a dip like that just by chance. once you articulate this, then now you do have to think about you have to think about the expected value of y. You can use the theorem from above, right? The formula. So it's n times standard deviation of the individual person. So if the vaccine had no effectiveness, on average, you see 99.5 people, right? That makes sense? You have 199 people, right? Just cut them in half. And then what's the standard deviation of capital Y?
Just do the same thing. 99.5 minus 57. Oh.
Are you close? So if you look at this formula up top, we're still using central limit theorem power 1. The standard deviation of the summation variable is the old standard deviation times square root of how many times you're flipping this coin. And so notice actually, nowhere in our work does this 200,000 come into play at all, actually. It's sort of interesting, right? All you're doing is processing, okay, I got basically 200 people have polio now, right? What's the probability that such a small number of them come from the vaccine group or not? So I don't know what this is. Anybody have those?
I got 7.05.
7.05. Yeah. Okay, so 99 minus that, you're 1 standard deviation away from the mean, right? That's like 91 or something, right? Minus again, you're in the 80s. Minus again, you're in the 70s. You got to minus the standard deviation off a lot to get there, right? So we're well outside of range of 3 standard deviations, which is why when we screw to the calculator, it's going to tell us the probability is 0. Let's just confirm that though.
We just use the standard. Okay.
Yeah, we're just going to scurry over here and be like, well, we expected to see 99.5 kids get polio from the vaccine group if it weren't effective, right? And then 7.05. And then what do we want to ask for amongst all this stuff here? Sorry. Yeah, below 57. Right now it's a left tail sort of thing. And you see how 57 isn't even close to being on this picture, right? 57 is way over here somewhere. There's like nothing left. And it tells me the probability is 0. So again, the probability is not actually 0. The probability is like 1 point blah, blah, times 10 to the negative 10th or something. You know, it's just minuscule. Okay, so all that to say, right? If the vaccine were not effective, the probability of seeing what I just saw is 0, or basically 0. That means the vaccine's effective, right? So a low p-value lets us reject this claim. And we do our double negative. If we reject that, that means we're saying the vaccine is effective. So it's sort of interesting, again, like the fact that you have 200,000 people per group, the only way that comes into play is like something like polio actually is not particularly contagious. So you need lots and lots of people to even get this many kids to get it, you know. But once you have this data right here, the initial sample sizes don't matter at all. So if you look at like the COVID vaccine trials, which I have as part of the homework, but if you look at the COVID vaccine trials, there'd be maybe like 50,000 people. They split them into 2 groups, you know, like 25,000 each or so, right? But then of those 25,000, barely any of them get COVID over the 6-month span, right? So you get the same kind of split like this, right? Maybe like from the vaccine group, like 10 people get it. From the non-vaccine group, maybe like 85 get it, you know? And then it's all sort of relative, right? What you're expecting was right in the middle of that. You didn't get right in the middle. You got like this, you got a big split. So anyway, this is how the central limit theorem part 1 is how you show that drugs are effective. It's rigorous mathematical, right? And you can quantify how strong the evidence is, right? So if that probability over there popped out at say like 4%, you know, a little iffy, right? You're saying there's like a 4% chance you would just see this from luck, you know? But there's not much ambiguous about a 0 popping out of this calculator here, right? If I close it. When the calculator pops out a 0, you're like, all right, I can project this. Okay, so that took me longer than I thought it would, as often happens nowadays. Any questions or comments on this first foray into actual statistics? It takes some getting used to, but it's super nice, right? So you pay a little bit of a price by learning the language, but I don't know. What you can do with it is really, really nice. All right, you guys have a good weekend. I'll see you on Monday.